So thank you very much for the invitation, and I'm very happy here at this conference in honor of Sylvia and Roger. I know them since a very long time because early on in my career I visited conferences on abelian groups and modules, and I met them there. And but that was only an aside in my career, and actually what I'm reporting on today is what kept me busy throughout my career. And I brought you the culprit here, phi, the Frobenius endomorphism. So this guy actually gave me a lot of research problems. Some of them have not been solved at all. I will tell you about that. And related to this guy is a phenomenon that appears in positive characteristic called the defect. So I am the man with the defects and bad places. You will see them later. And that has kept me busy throughout my career. And so defects appear in valuations, and I will start to introduce you by introducing you to valuations. Yeah, okay. Okay, so if you have a field K, then a valuation is a mapping from K to an ordered abelian group gamma together with an element infinity that is bigger than all elements of gamma. Gamma is an ordered abelian group such that, first of all, and I write this without parentheses, like this, v of x is infinity if and only if x is 0. Secondly, we have that V is a homomorphism from the multiplicative group to this group is additively written to that group, Vx plus Vy. And then what we call the algebraic triangle law, V of x plus y is bigger or equal to the minimum of V of x and V of y. And so that I write this additively and write the algebraic triangle inequality in this way means that I have a Kohl valuation, what we usually call a Kohl valuation. And so that's the first name that coincides with our first talk, Wolfgang Kohl, who did a lot for valuation theory. And examples. So one of the first examples that comes to mind is the Pierrick valuation. If you have A and B integers and B not 0, so you want a valuation on the rational numbers, you write A over B as A prime over B prime times P to the nu with nu in Z. So P is a prime such that P does not divide A and B. And then V of A over B is this nu in Z. And to every valuation, you have a valuation ring. OV, so that's the ring of all elements with non-negative value, unique maximal ideal MV. So OV modulo MV is a field, which we call KV. We write the V from the right. And these values here, we have, this is the residue field. And here we have a group, the group of values VK is the value group. So that's the image of the V in gamma, except for the infinity. Take that out. Okay, so here we have value group Z, and if you go to the residue field, you quickly find that the residue field is the finite field with p elements. Okay, so that's the Pierrick valuation, and here we have a completion that you know very well. This is the field QP of Pierrick numbers. The other example of valuations is the Ex-Addict valuation. We take K, any field, and we want a valuation on the rational function field Kx, rational function field. And what we do is we take the Ex-Addict valuation, which we define as follows. If we take a polynomial CiX to the I, then we take V of f to be the minimum of all indices such that Ci is non-zero. So that's the Ex-Addict valuation. Okay, this is only on the valuation on the polynomial ring. So if we have f over g, then V of f over g is V of f minus V of g. That's the Ex-Addict valuation on Kx, and here the completion is what we write as K double brackets X. Okay, so what is the value group? What's the residue field? Value group, obviously, again, Z, because here we have no minus, and residue field, here you can show is K. And that carries over to completions. Completions maintain the value group in the residue field. We will later call that immediate extensions. Okay, and in this class here, we have one particular guy. And now I should write an X, but I write a T because somehow, traditionally, for this guy, we write the variable as T, FPT. FPT, okay, FPT and QP, they both have value group Z, residue field FP. They are both complete discrete valued fields. So on the one hand, you would say, okay, complete discrete valued fields are the most wonderful that you have. And QP, yes, but FPT, no. If you ask the wrong questions, like model theorists do, what's the model theory of this guy? Yeah, then it turns out, okay, we know it for QP by the famous work of X-Cochen, and then independent also Yuri Yershov. So for instance, if you ask whether the elementary theory of a field is decidable, which means that in principle you have an algorithm that decides whenever you put in an elementary sentence, that decides whether this holds or does not hold. Decidability is proven for QP, and that was the mid-1960s by X-Cochen and independently Yershov. It's still an open question for FPT. So from the point of view of model theory, this is a monster. Many people have worked on that, including myself, and we are a little bit further than 1960s, but the problem is not solved. And the culprit is, it has turned out, and it has become, actually through my own work, the culprit is the defect. And I will show you in this lecture series why it is like that and what concretely the defect is destroying. Okay, now we have these two types of valuation, so we have a construction method, and then we need just one more piece of information. Theorem, also known as Chevaliers place extension theorem, is if you have a valuation on and L over K any extension, then V extends to L. And if you take this together with the two constructions that I have shown, what we get is that the only fields that do not admit non-trivial valuations are the finite fields and their algebraic extensions. Okay, so we have lots of valuations around. Now, a little bit about the origin of valuation theory. You could say it has three pillars. And in a sense, while number theory was the first, valuations were implicitly around already in the 19th century. But more explicitly, it came about first in the theory of ordered fields. And I should also add now also ordered groups. And the driving forces here were Hahn and Baer. Okay. Secondly, number theory. Driving forces, sure, Hensel, Hasse, and many more later. And algebraic geometry. Driving force here, Oskar Zariski. Now it's interesting to note that Hensel never worked with valuations explicitly. He never formulated valuations. It was somebody else who did it after reading Hensel. And so the development, the earlier development, so the first who gave the axioms that I wrote down was Kirchhoff in 1912. And then we have Ostrovsky. We have Krasner. Then very important Krull with his famous article Allgemeine Bewertungstheorie. And it's worth noting that Krull actually refers to these valuations here. He refers to the work of Artin and Schreier, which showed that there are arbitrarily big real closed fields. And these have non-trivial canonical valuations, and that was what led Krull to write his paper. And since we are in Brazil, I should not miss mentioning Paulo Riebenboim and Engler. And there's another guy, not to confuse with him, Endler, and so on. There are many, many people who developed valuation theory. Okay, so now I come to the second point. Extensions of valued fields. And such extensions I will write as, okay, you have a field extension, and then you have a valuation, which means the valuation lives on L, and you look at the restriction to K, so that's an extension of valued fields. And this gives, if you have such an extension, you have extensions of the value groups and residue fields, so you have canonical embeddings. Of V of K into V of L, and of the residue fields KV into LV. And it can happen that these are onto. So definition then the extension is called immediate. On the one hand, this is nice. We will see situations where we have very good immediate extensions. On the other hand, this is sort of sad because we are losing information from the extensions of the value groups and residue fields. So what's the opposite to immediate? It's a bit hard to formulate a working opposite, but one case is very interesting for us, and this case is described by the so-called Appianka inequality, which says that the transcendence degree of the extension is big or equal to the transcendence degree of the residue field extension plus, so to say, the transcendence degree of the value group extension. So, well, we are not so familiar with that, although the model theorists would make immediate sense of it. But here we say it's the rational rank of V of L modulo V of K, where the rational rank of an abelian group is defined to be the Q dimension of the so-called divisible hull. Okay, so maximal number of elements in V of L that are rationally independent of a V of K. And okay, this makes best sense if this is finite, but you can also read it with cardinalities, so cardinal numbers. It works as well. Okay, and definition, if it's finite, and we have equality, then V is an Appianka valuation of L over K. Okay, so that is in some sense the opposite case and to immediate, and in certain cases you can very well determine the value groups and the residue fields. I will not do that quite explicitly here, but I will mention one important consequence. Oh yeah, too strong today. Theorem. So, if we take an algebraic function field, with valuation, so valued algebraic function field, and V is an Appianka valuation of this, then the extension V of F, let's say modulo V of K, so as a group, is finitely generated, and same for the extension of the residue fields. And this is by no means always the case for if you take valuations on any algebraic function fields. Although the algebraic function fields are finitely generated structures, the extensions of the value groups and residue fields may not be at all. And that's also one thing that we have to fight with, both in the model theory of valued fields, but also in resolution of singularities. Okay, so now this is handling transcendental extensions. There's also an inequality that handles algebraic extensions, finite extensions. So if L over K V is finite, then we have the fundamental inequality. Which tells us that the degree of the extension, and we have again, like over there, we have big or equal sum. And now if you have a finite extension of fields, I should have said that before, then there are finitely many extensions V1 to Vg of V to L. And with respect to these, I have sum. So I have VI L over Vk. This is the so-called ramification index for the ith extension times the degree of the residue field extensions. That's the inertia index. Yeah, and we have this inequality. So the question is, what's missing? This is only an inequality. Can we make this into an equality? What's missing is, okay, quick answer, here comes in the defect. And let's look first, to work out the defect, let's look first at a finite extension such that the extension of V from K to L is unique. Okay, so this here was from 1 to G. So in other words, here we have the G. In other words, G is equal to 1. Okay, and then the lemma of Ostrovsky, or one thing before. No, that's okay. Lemma of Ostrovsky tells us, and now we get an equality, L over K is equal to E times F if the characteristic of the residue field is 0. And otherwise, we have to insert some power of P if the characteristic is P bigger than 0. Okay, and in this case, we define D, which is D of L over K. V is either the 1 that we have here or P to the nu, and it's called the defect of this extension. And if our D is bigger than 1, this is called a defect extension. Now for the next step we have to go back to our fundamental inequality, make it a fundamental equality. What's missing? We have a sum di times ei times fi, where di's are 1 or p, always the same p to the new I, but they can vary. And now the extension for this general case, without this assumption here, L over K V is a defect extension if di is bigger than 1 for at least 1I. And very important now, our field K with the valuation V is a defectless field. If it admits no defect extensions. Okay, so examples for defectless fields. First of all, by Ostrowski, if a field has residue characteristic 0, then it's always a defectless field by Ostrowski. Okay, Ostrowski, you have to go a little bit further here into these, where these di's come from, but it's resting on this. QP. FPT. So from that point of view, FPT is a nice valued field. And then, well, you can generalize these guys here into power series fields where you pick exponents from any order to be in group. They are all defectless. Okay, on the other hand, I have to familiarize you with the defect by giving you examples for defect extensions. No. No, that's something I hope that I will have in the end some time to come to that point. Okay, first example. And this example is said to be due to F-car Schmidt, which might be the same Schmidt as in Kohl-Remark-Schmidt, we don't exactly know. Otto Schmidt, okay, so not the same guy. Okay, so so we have already seen FPT. And now just take the rational function field Fp with 1 bracket, T, and in between, I probably don't have enough space for in between. So the transcendence degree here is infinite. It's even uncountable. So certainly we have one element S transcendental over fpt. And now we do for the following. We take fp ts to the p, fp ts. Okay, and now look at the value groups. Here it's Z, this is the completion, it's still Z. The residue field is fp. Here it's still fp. So consequently also these here have the same, so E and F are both 1, but the degree is P, so you get D is P. Okay? All right, I forgot. Next example is exactly answering your question. Because here this looks, when you see this, this was a very early example in the history of valuation theory. You might have a feeling now, oh, it's somehow connected with inseparability. But no, it's not. So here comes a second example, which is famous for algebraic geometers because it's an example given by Apjanka, except that Apjanka failed to identify the defect here. The example shows something else. Okay, so what do? We start with fpt. Now we adjoin pth roots of t, so for instance fp, well, let's call this guy k. 2. Yes, right, thank you. Yeah, actually you can do both. You can also do it with 1. K, no, that's right. T to the, well, yes, K, P to the N. And now you take the union over all of this, and what you get is the perfect hull, which I denote like that. Yeah? So you have a perfect field. I'll show you that it has a defect extension. So you take a root theta to the p minus theta minus 1 over t is 0. So that's the root of what we call an Artin-Schreier polynomial. So what we get is Artin-Schreier extensions. Okay, so go to k theta. What you easily show is now the value group here will be 1 over pz. So E is P, the degree is P, so D and F are 1. And still this here will still hold up here. Again, the value group, the ramification is P, inertia degree is 1, defect is 1. Now you go to the union here. What you find here is, well, what do you do with the value group? You make it P divisible. Yeah? You still have, so you get value group 1 over P to the infinity Z. You still have residue field Fp. Yeah, so here the value group is the same. So this is the value group for both of them, and this is for both of them. So the extension is immediate, so the defect is P. And you see the defect appears through a separable, namely an Artin-Schreier extension over a perfect field. And what I want to tell you later, if I have enough time, so this is a defect that is independent of purely inseparable defect extensions. And others there are that come through transformation. You can, under certain conditions, you can transform purely inseparable defect extensions into separable defect extensions that would be dependent defect. So, but that's something for later. Okay, and as a third example, QP. QP is defectless. But no way. You will not get away from defects. If you, well, if you do algebraic number theories, you always stay nicely within finite extensions. And a finite extension of a defectless field is defectless. But if you do infinite extensions, of QP, they can be non-defectless fields. So for instance, you may have heard about, came up in the last decade or so, the deeply ramified extensions of QP. These will deliver such bad fields. Okay, good. So far about the defect. And yes, I guess one more thing before we come to the next subject. So when we have to fight the defect, we have basically two possibilities. Either show it's not there, or work around it. The first theorem that I want to show you is one of these cases where you show it's not there. So take an f over k algebraic function field with Apjanka valuation. If kv is a defectless field, then so is the function field itself. And that's a theorem that I proved actually in my thesis, and it was published much later in 2010. And that's one of the fundamental theorems that I will use later for results about resolution and about the model theory of valued fields that I will tell you about. Okay, now is the time for the slide. Do we still have time? Yeah. Okay. Oh, I forgot to say, please ask questions within the talk. No question period. Question period cancelled. Absolute ramification theory. Yes, we have to get on the, just go on. Yeah, minimize it, it's okay. Minimize, yep. Oops, what's that? Minimize that. We just need the desktop. Just go to the desktop. Close it, close it. Okay, and now, yeah, here, FEK. Okay, and that one. Okay. Thank you. Does everybody agree? Okay, so is the projector working? Nope. I think we have to switch it on from here. Is that the projector? Yes. Where's the projector? Here. It turned green? Okay, then it will come. Okay, so what we will do now is, you may have heard about the term absolute Galois theory. So, or absolute Galois group. So for instance, the very big riddle in number theory, what is the absolute Galois group of Q? Meaning it's the automorphism group of the algebraic closure over that field. Yeah, so that's the absolute Galois group. And Okay, we have to get this away. Okay, good. So, yeah, before I scroll further down, we take, no, that was, okay. Oh, wonderful, very good, good. So we start with a non-trivially valued field. We can stay with that. Yep. Okay, non-trivially valued field. And we have to say something. We define what we call the characteristic exponent. So if it's if the characteristic of the residue field is bigger than 0, we take that prime to be p. Otherwise, we set p equal 1 and not 0. Okay, and now we look at the absolute Galois group of, okay, this is on the left side, you have the Galois groups, then come the fields themselves, value groups, and residue fields. I have to scroll down to a, so here we are. You see all that? Good. So now it's often done wrong by a number of theorists to take the fixed groups of the so-called ramification groups, which I will not define. They don't play so much of a role now. So we have 3 ramification groups, and usually the fixed fields are taken to be in the algebraic closure. But it's better to take them in the separable algebraic closure of L. So these are the fixed fields. So first of all here, that's the smallest ramification group. We have the absolute ramification field. Here we have the absolute inertia field. And here we have the absolute decomposition field, which happens to be the Henselization. What's the Henselization of valued field? It is it's an algebraic extension of the valued field so that its valuation ring is Henselian in the sense we heard already today, and such that this embeds into every other Henselian field, every other valued field with a Henselian valuation. So these two are the same fields. And by the way, for the algebraic geometers call the absolute inertia field the strict Henselization. And that's for a reason that we will see a bit later in the next talk. Okay, so what we have here is the Henselization is an immediate extension. That's a nice thing. Then you go up to the inertia field, value group remains the same, and here you get the separable algebraic closure of the residue field. And the whole thing is Galois, like this extension here. Then in the next step, you go to the absolute ramification field. Here the residue fields remain the same. And what you do to the value group is you divide, and here I say 1 over p prime to infinity. The p prime indicates all primes that are prime to p. So you divide by all primes that are not equal to p. Okay, so that's the absolute ramification field. Then here we get an extension where we do the remaining division, and also the remaining extension for the residue fields. Namely, we can go up here, and that's where we need that V is non-trivial. The fact is, while you are only here at the separable algebraic closure, you get the algebraic closure of the residue field. And you get the full divisible hull of the value group of L. And then beyond that, so the purely inseparable part here, value group and residue field remain the same. Now there's a very nice thing in ramification theory. This group is a P group, which makes this here a Galois P extension. So, and that means that every finite extension is actually a tower of Artin-Schreier extensions, if we are in positive characteristic, or Galois extensions of degree P, which are Kummer extensions in if the field itself has characteristic 0. Okay, so that's our scheme of absolute ramification theory. Now, I didn't note in this one here, but I can show you which extensions are defectless. So, well, it must be finite extensions that you look at. And in fact, if you take any finite extension sitting between this and this here, yeah, this is the Henselization, which also means it's also equivalent to be Henselian. It's also equivalent to that the extension of the valuation to the algebraic closure is unique. So everything here in between has unique extension of the valuation. Now, if you take a finite extension of field sitting somewhere in between here, it will always be defectless. Yeah, and if you add this part here, well, then you have possibly more than one extension, but then it's defectless in the more general sense that all the di's are one in the general fundamental inequality. So this is the defectless part here. Yeah, and here the defects appear. So that means if we are forced to work with this here, then we are working against the defect. Now, another thing is, if you're a little bit familiar with the notion of tame ramification, up to here is all tame ramification, beyond that is wild ramification. We say this is the maximal tame extension of our L, and everything else is purely wild. And okay, we'll come back to that. And the history of resolution of singularities. So as long as one could work inside here, which means if you have residue characteristic 0, then actually this field is the algebraic closure. Nothing here beyond. So this is the algebraic closure. So if you have residue characteristic 0, you're only working with this here. Everything is defectless. But not everything is unramified. You have the ramification up here. And that's what you have to fight against when you do resolution of singularities over fields of characteristic 0. But I will tell you more about that in my next talk.